to the preparatory training for BOE certificate examination. This is the tutorial 2, part 2 of steam properties. Now, if you have gone through the part 1 of this topic, that means you can now calculate the specific enthalpy of steam, the specific volume, and the specific entropy using the steam table. You also know the relationship between the temperature and enthalpy of steam. Now, in this part, we will first start with solving few problems related to properties of steam. Those are the typical problems. And further on, we will discuss about the concepts of internal energy, the throttling process, and the constant volume process. So let us start with a few problems. When you see a problem, first read it carefully and try to find out which are the points which are to be noted, particularly in this problem. Now, 20 meter cube of steam is at a pressure of 10 bar, having dryness fraction of 0.95. So you know it's a wet steam, the pressure is known and the dryness fraction is known. Now this steam loses 2000 kilocalorie of heat at constant pressure. Calculate the dryness fraction of the steam after the completion of this process. Now, few things are required to be, you need to be careful about this. One is that in this question, the volume of the steam is given and not the quantity of the steam in kg. If you remember the steam table where the specific enthalpy, specific volume, everything is given on the basis of per kg of steam. So the first thing which we need to do is convert this volume into mass of steam. Second thing is that 2000 kilocalorie of heat is lost by this steam. And if you are having a steam table of kilojoule that is in a SI system and you are calculating everything in a SI system, you must not forget to convert this kilocalorie into kilojoule before doing any calculation. The third thing is that even after losing the heat, the pressure doesn't change. So the 10 bar remains 10 bar, right? So first thing what we do is we take our steam table and do not forget to write this particular sentence assuming the pressure given is absolute, because it is not mentioned in the problem that the pressure is absolute. So we can assume the pressure is given as absolute and then we can refer the steam table at 10 bar and we can note down the sensible heat of the water, the latent heat of evaporation HFG, and the specific volume. Now, once we know the specific volume, we can convert the volume of steam 20 meter cube into its equivalent mass. So specific volume, we divide the volume with specific volume. Do not miss that this was a wet steam and the specific volume is not Vg, it is XVg. So do write XVg instead of Vg and take the dryness fraction into consideration. So we now know the mass is 108.35 kg. We can find out the enthalpy of this steam because the pressure is known, the dryness fraction is known, and we know the enthalpy of wet steam can be calculated as HF plus XHFG. So we calculate the enthalpy of this wet steam before the heat loss. Now this 108.35 kg steam is losing 2000 kilocalorie heat. So first thing we need is how much heat is lost by per kg of steam. So heat loss per kg of steam, we convert the kilocalorie into kilojoule and then divide it by the mass to get the heat lost by the steam per kg. Now after this loss of heat, the new enthalpy of the steam we can calculate as 2598.23 kilojoule per kg. Now this was already a wet steam and it has lost further energy. Therefore it will be still a wet steam with a dryness fraction less than 0.95, that is. So now we set the equation of wet steam again, HF plus XHFG. In this case X is unknown. Since the pressure has not changed, the HF and HFG remain same. So from this equation, equating the new enthalpy, we can calculate the dryness fraction as 0.91. This is a very typical problem and it's not very difficult to follow. Okay, another problem. Two boilers A and B are delivering steam in equal amount to a common header, both at a pressure of 15 bar. Boiler A has a superheater, boiler B doesn't have a superheater. The temperature of the steam supplied by a boiler A is 300 degrees centigrade, which is having a superheater. The temperature of the resulting mixture of the steam in the common header is 235 degrees centigrade. What we need to find out is the quality of steam that is supplied by boiler B, which does not have a superheater. So what we do, we just make a freehand sketch of this A, B delivering the steam to a common header. We know that both boiler A and B is 15 bar, so common header pressure would be again also 15 bar. So assuming the pressure given as absolute, we refer the steam table and note down the details of this particular steam. Do not forget to take down the saturation temperature because we are dealing with superheated steam here. So the saturation temperature is 198.3 and then we did the further HF, HFG and HG. Once we know the saturation temperature is 198.3 for 15 bar, we immediately understand that the common header steam, which is having 235 degrees centigrade temperature, is again superheated quality of steam. And since boiler B does not have a superheater, most likely it is going to be a wet steam. The dryness fraction is unknown, which we need actually to find out. So let us assume it is a dryness fraction X. Now using the heat and mass balance, first we understand that both are delivering equal amount of steam. So if boiler A is supplying 1 kg, boiler B is also supplying 1 kg. The total quantity of steam will be in the common header will be 2 kg. So now we use the heat and mass balance. Enthalpy from boiler A plus enthalpy from boiler B will be equal to enthalpy from in the common header steam. Now boiler A is superheated steam. We can find out the enthalpy of superheated steam as Hg plus Cpt sub minus Tsat. Just remember, in BOE examination, if steam table is provided, particularly with superheated steam table, always calculate the superheated steam enthalpy from the table and do not use this formula Hg plus Cpt sub minus Tsat in that case. Anyway, let us assume that the steam table is not given, so we calculate it as Hg plus Cpt sub minus Tsat. Boiler B will be wet steam, so HF plus XHFG. HF HFG is known, X is unknown. And common header C is again superheated steam, so again Hg plus Cpt sub minus Tsat. Only thing is in this case the mass will be 2 kg. So from this equation the only unknown is the dryness fraction X, so we can calculate the dryness fraction X as 0.97. Let us move forward from here to problem 3. Again, this is a typical problem. Suppose the steam velocity is given, the steam flow is given, they would ask you to find out the pipe size, the diameter of the pipe. So find the suitable size for a pipe to carry dry saturated steam at 150 degrees centigrade. So it's a dry saturated steam at 150 degrees centigrade. The pressure is not given, but we can always refer the table 1 of the steam table, which is temperature based. At 40 kg per second, that is the mass flow is given, and assume steam velocity as 140 km per hour. So in this case, when they ask the size of the pipe, it will be basically the diameter, because the pipe size is specified by NB, nominal bore diameter. Now we know that the diameter, which is from where we can calculate the area, and area can be calculated if I know the volumetric flow and the velocity. So diameter is pi d squared by 4. Then A is equal to Q by V, where Q is the volumetric flow in meter cube per second and V is the velocity in meter per second. Now in this particular problem, the Q is given as mass flow, right? So first we need to convert this mass flow into volumetric flow, and for that we need the specific volume of this saturated steam at 150 degrees centigrade. So we refer the steam table, that is the temperature based steam table, and we find out the specific volume of saturated steam at 150 degrees centigrade is 0.39245 meter cube per kg. At this point, let me just tell you that when we are noting down the specific volume of steam, take as many digits as possible after the decimal, which is mentioned in the steam table, right? That will make the calculation more correct, because as it is, the specific volume will be much less than 1. So now from this specific volume we can calculate the volumetric flow from the mass flow. So we multiply mass flow into specific volume to get the volumetric flow in meter cube per second, and the velocity is given as 140 kilometer per hour. So we convert that into meter per second by dividing it with 3.6. And since now the Q and V both are known, we can find out pi d square by 4, that is area, as 0.404 meter square. And from there I can calculate the ds, 0.717 meter. You can very well keep the answer as 0.717 meter. But suppose they ask you in terms of inch dia, right? Then remember 0.7 meter is 28 inches, right? And 0.717 meter is more than that. And if you select 29 inches, that will be very impractical, because you do not get 29 inches diameter pipe in the fill, right? So you have to select for the next higher size, that will be 30 inch diameter. Okay, now we go to the next problem. Water from a drum at a pressure of 15 bar is flushed to a lower pressure of 2 bar. If the water flow rate is 1000 kg per hour, calculate the percentage of flush steam and the flow rate of flush steam. Now I believe you are aware about the flush tank for the CBDs, usually what is you find in the fill, right? So in that case, the CBD water, which is from the drum, is taken down to a tank which is at a lower pressure. In this case, the lower pressure is 2 bar and the drum pressure was 15 bar, and some amount of water, which is saturated water, will flush into steam, right? They want us to find out the percentage of that flushing and the flow rate, if the 1000 kg per hour is the flow rate for the blowdown. So what we do is we first take down the TH diagram, and in the TH diagram we draw an imaginarily 15 bar pressure line. CBD would be taken from here, right, which will have the total specific enthalpy of saturated water, HF. Let us say it is HF1 for the higher pressure. Now this is taken to the flush tank where the pressure is 2 bar. Now the first thing we note that at 2 bar, the saturated condition water will have a much lesser enthalpy, HF2. So we have some additional enthalpy, HF1 minus HF2, which is going to convert some amount of water into steam. Now in a steam table, whatever is the specific enthalpy of evaporation at 2 bar, HFG2, let us say, if we give that to 1 kg of water, then we are going to get the total 1 kg of water converted into steam. In this case, the additional enthalpy is HF1 minus HF2. So naturally, the percentage conversion of the water into steam will be HF1 minus HF2 over HFG2 into 100. So now, in this problem, from the steam table, assuming the pressures are given in absolute, we take down the HF1, HF2 and HFG2 from 15 and 2 bar, right, respectively. HF1 for the 15 bar condition, HF2 and HFG2 is for the 2 bar conditions, the lower pressure conditions. So using the same equation, we get the percentage of flush steam will be 15.44%, and if 1000 kg per hour is the flow rate for the blowdown, then the flow rate for this flush steam would be 15.44% of 1000 kg, that will be 154.4 kg per hour. Okay, now what we do is we take a look at the concepts of, let us say, first internal energy, and then we will go to the throttling of steam, and finally the constant volume process. Now, whenever you have certain expansion of volume taking against a certain pressure, you have to do some work, right? And this work can be calculated by multiplying the pressure into volume. If the work is in kilojoule, the pressure would be naturally in kilopascal and the volume will be in meter cube. So let us take, say, the atmospheric condition. If I take the steam, then if water is converted into steam, there will be a very large expansion in the volume, right? And if we consider that 0 degree centigrade of water under atmospheric pressure is converted into steam at 100 degrees centigrade, then the specific volume of atmospheric pressure will be 1.67 meter cube, and the specific volume of water at 0 degree centigrade we can assume as 0.001 meter cube, that is 1000 kg per meter cube density. Now the first thing you can note here, that when you try to find out the change in volume, the water volume, if we deduct from 1.67 meter cube, it will still remain 1.67. So we can very well neglect it. So change in volume will be the volume of the steam, basically. So if I consider the work done, then it will be PV, where the P is the atmospheric pressure, P in kilopascal, 101.3 kilopascal, and the change in volume is 1.67. So 169.17 kilojoule will be the work done. But if you consider that how much heat has been added, energy has been added, then at 0 degree centigrade the enthalpy is 0. So total Hg amount of heat at atmospheric pressure, which is 2676 kilojoule per kg, is added to this water. That means we find a difference that the whole amount of this energy is not doing the job. The work is done only by the part of this energy. So you can conceptualize internal energy as the difference of this, or rather the part of the energy which is not doing any work, right? So you can deduct from the enthalpy, the work done, you get the internal energy. So U is equal to H minus P. So with this concept, we can calculate the internal energy of dry saturated steam. Change in enthalpy is Hg. Pressure, whatever you take. If you are referring the steam table in SI unit, that will be in bars, so do not forget to multiply it with 100. And the change in the volume, as I told you, or we have just seen that the water volume does not count, so the total Vg will be the change in volume. Similarly, the internal energy of wet steam, let us say with the dryness fraction of X, can be calculated as the enthalpy of wet steam minus pressure into specific volume of wet steam, that is HV. And for superheated steam, it will be the enthalpy of superheated steam, that is Hg plus Cp T sub minus T sat, minus pressure into the superheated volume, that is Vg into T sub by T sat. But in BOE calculation, most of the time you will be sometimes, or rather in few questions you will be required to ask, find out the change in internal energy, right? So rather the change in internal energy you can remember as del U is equal to del H, that is change in enthalpy, minus P delta V. Delta V is the change in volume. Okay, we move on from here and see the concept of throttling. Now whenever a steam pressure is reduced, it is done through throttling, right? And one thing is considered, that in throttling process, the enthalpy before throttling and enthalpy after throttling remain same, right? And actually this particular concept is used when we want to find out the dryness fraction of a wet steam, unknown dryness fraction of a wet steam by a throttling calorimeter. Because see, the temperature of the wet steam doesn't tell us much. It is always saturated temperature, whether the dryness fraction is 0.9999 or 0.0001. The temperature is always the saturated temperature. So what we do, we use a throttling calorimeter and we throttle this wet steam to a lower pressure. So again, take the reference of a TH diagram. Let us say this is an imaginary 15 bar pressure line, and we have got a steam with the dryness fraction x here. Since x is not known, we cannot calculate the h weight, or vice versa. Since h weight is not known, we cannot calculate the dryness fraction x, because 15 bar we know the corresponding HF and HFG from the steam table. So what do? We throttle it to a lower pressure, let us say 2 bar. The moment we are throttling it 2 bar, the amount of enthalpy it is having in the wet condition at a higher pressure is enough to increase the temperature of the steam above the saturation temperature of 2 bar. So we are going to have a superheated steam, right? Now we know the Hg of the 2 bar pressure line from the steam table, and since we have a new temperature which is a superheated temperature more than the saturation temperature of 2 bar, we can also calculate this part of the heat, that is Cp T sub minus T sat. So now we can equate HF plus XHFG at 15 bar with Hg plus Cp T sub minus T sat at 2 bar, right? And we can calculate the dryness fraction X, right? Number of problems would come where you'll be given the throttling pressure. You just have to mention one line, assuming the enthalpy before and after throttling remains constant. Okay. Now we go for the concept of constant volume. Now imagine there is a boiler which is stopped, that is the firing is stopped, and the MSV is closed, right? So this is boxed up in unfired condition. The pressure is P1 and this is a superheated steam, so the temperature is T1, let us say. Now since the firing is stopped, gradually because of the heat loss, what is going to happen? First the temperature is going to drop, and correspondingly the pressure is going to also drop, right? So as the heat is lost to the surrounding, both the pressure and temperature is going to drop. But two things are not going to change. One is the total amount of steam, the mass of the steam, which is not going to change because no steam is getting added and no steam is going out. So the mass of the steam will remain constant, and since the MSV is closed, the volume is also constant. The total volume is constant as well as the total mass is constant. So therefore we can say the specific volume is also constant because specific volume is V by M. Now if I allow it to continue like this, gradually the heat will be lost, and at one point of time we might have a condition where we will have a saturated steam inside, and let us assume at a pressure of P2, and the temperature will be the corresponding saturation temperature of P2. If I allow further heat loss, now the steam will become wet, but there will be again reduction in pressure. As the steam will become wet and wet, the pressure is going to get reduced further. So further loss of heat will get me a condition of wet steam. Let us assume at a pressure of P3, and the temperature of the wet steam will be the saturation temperature corresponding to the pressure P3, right? Now the specific volume, if we calculate in these three conditions separately, the superheated specific volume will be Vg into T sub by T sat at pressure P1. Vg will be taken from the steam table corresponding to pressure P1. The saturated steam will be naturally the Vg correspondingly to the pressure P2, and the wet steam condition, the specific volume V3 will be XVg, where the Vg will be taken from the steam table corresponding to pressure P3. And since the specific volume is constant, we can easily say V1 will be equal to V2 will be equal to V3, right? Now let us see a problem where this particular concept would be used. Steam at a pressure 18 bar, the dryness fraction of 0.9, that means this is the wet steam, is heated at a constant pressure. So again, constant pressure means after the heat is added, it will still remain at 18 bar until it becomes dry and saturated. Find the increase in the internal energy. Second part is, if the volume is now kept constant, That means after it becomes saturated, now the volume is kept constant, and suppose some heat is extracted, heat loss you can say. So how much heat should be extracted to reduce the pressure to 1 bar? So first thing is that if it is a wet steam with a dryness fraction 0.9, that means what is it is lacking? It is lacking in HFG of 0.1 fraction, because if I give 0.1 HFG, it will get the full HFG and it will become dry saturated. And if you see the volume at 0.9 dryness fraction, it is XVG. At dry saturated condition, it will become VG. So what we are adding is basically 1 minus X, that is 0.1 VG. So first part we find out the change in the enthalpy, that is 1 minus X into HFG, and the change in volume, that is 1 minus X into VG. And we can use this in the equation known as the change in internal energy del U is equal to del H minus 100 P delta V. Here the del H we know is 0.1 into HFG at 18 bar, and del V will be 0.1 into VG at 18 bar. So from the steam table, again do not forget to mention this, assuming the pressure given is absolute, we note down the HFG, HG and VG at 18 bar condition. So using this, increase in internal energy will be 0.1 into del H, that is HFG, and 0.1 into VG, that is the del V. So the increase in internal energy will be 171.17 kilojoule. Now in the second part of the problem, once the steam becomes dry and saturated, some heat is lost until the pressure becomes 1 bar, and this process is a constant volume process. That is, the volume is not going to change. Now, since the steam was already saturated and is losing some heat, it will naturally become weight. The dryness fraction is unknown in our case. And since it's a constant volume process, the specific volume will remain constant. So V2 will be equal to V1, and that will be the same as the VG at 18 bar pressure, which is 0.11033, which we have already found out from the steam table. So using the equation of specific volume of wet steam at 1 bar pressure, we take the steam from the steam table, the corresponding HF, HFG and VG, and equating the wet steam VG, that is V2 x VG, we can find out the X as 0.06514. It becomes very weight actually. And since it is 1 bar, that means it has already gone into vacuum, if you understand that. We should have opened the drum vent much earlier than this. Anyway, now since the X is known, we can calculate the enthalpy of this steam as HF plus XHFG, and once the enthalpy is known, we can find out how much heat has been extracted by deducting it from the Hg at 18 bar condition. The answer will be 2230.22 kilojoule per kg. That will be the answer of the part 2. With this I conclude the part 2 of this tutorial. In the next tutorial we will deal with a new subject, that will be combustion. So we'll be talking about fuel, its various properties, the combustion mechanism, the calculation of GCV, NCV, and the calculation of air and the gas property, gas compositions. Right? Till then, thank you very much. See you next time.